Okay, so module 2 of COA, we are going to do the revision. So if you haven't watched the complete video of module 2, there is a playlist separately in our channel, so you can just go and watch from there. This is just the revision section, so I will be more fast in here. Okay, so first we will discuss what is computer architecture. So in computer architecture is mainly defined by two things. The first thing is the instruction set, and the second thing is the architecture state. Instruction set means it includes the commands and operation that the processor can execute, that the processor can understand, execute. So all of the commands and operation the processor can understood is there in the instruction set. And the second thing is the architecture state. Architecture state is a snapshot. If I'm taking a photo of the current processor state, that is called as the architecture state. So computer architecture is basically defined by these two things. We have the instruction set and we have the architecture state. Now, architecture state is like basically consists of two main things, that is a program counter and general purpose register. There are 32 general purpose register in RISC-V architecture. Now, program counter means which is going to give the address, memory address of the next instruction. Now, I told you there are 32-bit general purpose register. So, since I'm talking about 32-bit central purpose register, that is X0 to X31 are the 32-bit general purpose register. These contains the data in which the CPU, in which the ALU would work on, do the operations and all. That data is present in these general purpose registers. That data would be temporarily stored in this register which CPU is working on. So the data in which CPU is working on is temporarily present or stored in these registers. Okay, now all of these values in the register can be changed because they are temporarily stored there. But X0 registers is basically hardwired to 0, means X0 register always has 0 in it. It is like their value, X0's value won't not change. It would always be 0. Fine. So the next thing is that we have to understand why the RISC-V has such architecture state, program counter, and what is the main importance of is that, you know, whenever a software is coming, the software would assume that the RISC-V has this PC and 32 register, and it makes it more compatible, right? It ensures compatibility here, and also preventing, or it makes sure that the program run correctly. So PC and 32 registers are needed to make sure that the program is running here correctly. So that is one important thing that you have to understand. So if you are doing any implementation of RISC-V, they must have this PC and the 32 registers, because without this, the software which is coming here would come here to this processor by assuming that this PC and registers are there. So without them, the program cannot run properly, and it is basically ensuring the compatibility. Now let's see how the execution works. So whenever at one particular current architecture state, there would be a program counter value and the data stored in the register, and then the architecture state would again change. So in the next architecture state, the new PC value and the new registers, modified registers, you are going to see in the new architecture state. So in every architecture state, the program counter and registers value would be different. Understood? Now RISC-V instruction, you have to understand there are different RISC-V instructions here. Okay, so you have to understand one important thing here before that RISC-V instruction. We will come back. There is more slides for detailed explanation later coming. So right now you can understand the microarchitectural design process. Now this is going to talk about that CPU's microarchitecture. How is basically it is designed internally. Okay, internally it is designed how the CPU's microarchitecture is designed. There are mainly two paths, the data path and the control path. Data path means what you are able to see, the ALU, the memory, the registers and all. Control part is that if you have a multiplexer, the multiplexer has to select between two paths. The memory write signal, the memory registers enable signal. These are the control units. So data path means what? The muscle of the CPU, that is which is moving the data, processing the data and all. Like memory, they store the data and instruction. Registers is a small fast register which is storage thing which is there in the CPU. And ALU is doing the arithmetic logical operation. Multiplexer is going to select between two input signals. It will select one signals. So the muscle of the CPU is a data path. Data path means memory, ALU, the multiplexer, the registers and all are the data path parts which are there in the data path. Control unit is the brain, the main working. Whether you have to write in the memory, then I have to memory write signal should be enabled. right? If I wanted to, in the registers case, if I'm just checking that registers, I have to, register has enabled signals, read or write enabled signals are there. So that signals, multiplexer select signals are there to select which input we have to go, which path you have to choose. So this is decided by the brain, right? That is a control unit. So the data path and control path is there. That is what we are talking about. So CPU's microarchitecture is organized into two, that is the data path and the control unit path. Okay, so here if you see, let's then the next thing is like how you can design the CPU, like in this model how you can get the CPU. Okay, so we will be starting with the state element. The design begins with the hardware that holds the state, which include the memory, which store the instruction and data. Then architecture state, program counter and registers are there. So first we are going to start with the state elements. State elements are those hardware that can hold the data and which include the architecture state. And we know in architecture state we have program counter and registers. So first when you are designing a CPU, first we will start with implementing the state elements. Okay, state elements, the hardware that is holding the state. So those hardware which is holding the state are the state elements. So that we have to first construct. Then we are going to add the combination logic. State, a combination logical between these states means combination logic blocks, like we will place the ALU, muxes and all between the memory and the state, that is PC and the registers. We have to place this. Now their job is to take the current state, compute the next state as output, that is taking the input, computing it, that is mainly the logical arithmetical operation. That block we have to place in between of this state element block. You're going to place this computational logic block also. Okay, so you have understood that the memory, one important thing is that there is instruction memory and data memory. Instruction memory is the storing the program instructions and all. Data memory is the operands, like some variables and all will be there, no? Some data and variables that you can read it by load and you can write that using the store. Those things are there. So memory is basically partitioned into two. Instruction memory, which stores the program, that is the read only during instruction. The instructions are basically read only, right? We are just able to read the instruction only. Then you have the data memory, which contains the variables. You can read the variables or you can write to the variables, to the data. You can write some data to a particular location in the memory. So that is data memory. So you have to understand this separation avoid conflict. The CPU can fetch an instruction and read or write data simultaneously. So why this memory is partitioned into two? You have instruction memory and data memory. So the question can come, why the memory is partitioned into instruction memory and data memory? To avoid conflict. So the CPU can read the instruction as well as read or write operation of the data can also happen simultaneously, and this architecture is known as the Harvard architecture model. Harvard architecture model means in Harvard architecture model our instruction and data memory are separate to avoid the conflicts. So such architecture is the Harvard architecture model. Okay, so while you are designing the CPU, first you will do the state element. State element means the memory and the architecture states, PC and the registers. Then we will do the combination logic. We will add the combination logic between them. The next thing we have to understand the memory. We will partition the memory into two. That is the instruction memory is also there, data memory is also there. This is the what the Harvard model actually says. Now why we are partitioning the memory into two? To avoid the conflict. So in order to avoid the conflict, we have partitioned the memory like that. Fine. Now the next thing that you have to understand is this figure. Okay, so first we have the program counter, and I told you the memory is there. Okay, program counter, memory, the registers, that is the register file. Okay, now we will place in between them, these are the main four state elements. What I told you, the register, the memory and the program counter are the state elements. So first I have to place the program counter, then my instruction memory is there, then also data memory is there, and register file is there. So we have to understand each of them. Here if you see, there are different lines here. Heavy lines are there, medium lines are there, narrow lines are there, blue lines are there. Heavy lines is talking about 32-bit data bus is this heavy line. Medium lines are narrow bus, that is 5-bit address. address registers are narrow lines. Medium lines. Narrow lines are single one line. This is narrow lines. There are blue lines which is also describing the control signals. WE3 and all are blue lines. So this 32-bit data 32-bit data bus is this heavy lines. Then there are medium lines. The medium lines are basically the 5-bit address. 5-bit address. 32-bit data bus is the data bus is this heavy lines, and narrow is the 5-bit address. Right, 5-bit addresses, and there is single 1 bit, that is basically the blue lines. The control is basically shown by this blue lines, and single line is also there. 1 bit wire. So heavy line is 32-bit data bus. Then middle line is that is basically the 5-bit address. Fine. Okay, cool. Now you see the program counter here. Program counter. Now program counter, what it do is it would give the instruction, and the next instruction would get updated here. That means point to the current instruction address, and PC next is the input. We tell the PC what address is coming next. Usually PC plus 4 or a branch or jump target computed by the computational logic. Now here if you see PC, the PC value is the which would give the instruction, current instruction which you wanted to put here. Okay, and if you wanted to calculate the next instruction, the input is PC next. Both are 32-bit. You can see 32-bit data buses and clock signal is there. So this is how here if you see PC is the, then PC nest is there, then we have the clock. Okay, 32-bit why we are having this is because 32-bit heavy lines are this 32-bit data bus. Okay, so this would input the next instruction, that would come out the instruction that is needed. Now the PC's next instruction is basically computed here. That computation is what it's like there would be some computation part would be there. They would calculate this and plus 4. It will do that instruction plus 4 in order to calculate the next instruction, to give the next instruction. That part would be here, that would be discussing, we will discuss later, but right now we are just discussing the state elements. Then you can see the instruction memory. It has a single read port, RD. Okay, so you can see that there is a single read port. Input A is a 32-bit address which is coming from the PC, and output RD would give the 32-bit instruction which is stored at that address. Okay, and no write enable, it is treated as a read only during program execution. So instruction memory is that it will actually take the input of this 32-bit address, and that address corresponding instruction at that address, the PC would give the address of the instruction. That address is passed through the instruction memory, and RD would give that RD would give whatever is there in that instruction, that whatever is there in that address. So on that address, if you have an instruction, that instruction is coming out from the RD. One read port is there, a single read port, right? And that 32-bit instruction stored on that address we will get through the RD. There is no write enable signal and all, because we don't want to write here. Instruction memory is a read only, we don't need to write anything in the instruction memory, right? So this is about the PC and the instruction memory. Now we have the register file. If you see the register file, A1, there are two read port. Okay, that is A1, A2 are the read port. Now A3 is a write port. One write port is there. Okay, let's understand this. A1, A2 would take the value from the instruction. It will take the RS1 and RS2 value. Okay, and what it is going to do, that in that RS1 and RS2 at that address, what is the value here in that address, that is given through the RD1 and RD2. If I want to write anything to a register, that address I will give it through the A3, and WD3 means the data that I wanted to write, 32-bit data bus, right? That data which I wanted to write in that register of the A3, I will give it in the WD3. So WE3 enable signal would be 1. You can detailedly understand this when you are seeing from the playlist. This is just a quick summary part, I would say it very fastly, right? So here you have A1 and A2, which would contain the address of the registers, and their value is through the read port RD1 and RD2. So RD1 and RD2 would read the data output from this address register. Now A3 means what? If I want to write anything to a register, which register I want to write, that is A3. WD3, the data that I have to write here. So these are 5-bit. RD1, RD2 and WD3 are all 32-bit. Okay. Now my clock signal and WE3 is 1 bit. That would be enabled when I wanted to write something. If I want to write something to a register, then my WE3 value would be enabled signal. Fine. This much we have understood. Okay. So address, whenever this registers case is coming, now we have a 5-bit register.